Okay, let us start. Hi, everyone. Thank you for joining. Welcome to Bcast, a series of presentations on high-performance computing and parallel programming organized by Scala Parallel Computing Laboratory, led by Thorsten Heffler at ETH Zurich. Today, we have with us Virginia Smith. Virginia is an assistant professor in the machine learning department at Carnegie Mellon University, and her research focuses on machine learning, optimization, and distributed systems, with an emphasis on addressing challenges related to optimization, privacy, and robustness in distributed settings. Virginia has received a number of awards for her work, including the NSF Career Award, MIT TR35 Innovator Awards, Inter Rising Star, and faculty awards from Google, Apple, and Meta. So without further ado, I'll leave the stage to you, Virginia.
Wonderful. Thanks so much for the invitation. I'm really looking forward to speaking with you all today. And I'd love to make this, interactive. So if there's an easy way, maybe you could put questions in the chat window. Please stop me if you have questions along the way. Would love to, make this a discussion with folks. So as was introduced, a lot of my work is broadly in machine learning and distributed systems, but more recently I've focused a lot on the problem of federated learning. So today I'm going to be talking about the problem of evaluation in large-scale machine learning systems, and I'm going to speak first about evaluation in the context of federated learning, and then I'm going to talk a little bit more broadly about some tools we've been developing for evaluation of large language models. So just as a little bit of more background for who I am and some of the research in my lab, kind of the key motivation for the area of federated learning is very simply, if you think about existing applications of machine learning, you might be thinking about things like these language models, or maybe the application of voice recognition in phones, or things like machine learning for healthcare, or smart homes, or smart cities. Crucially, all of these applications rely on data in one form or another. And these data sets are not usually coming from, say, a single mobile phone user, or a single patient within a single hospital, or a single sensor in a smart home or smart city. They're coming from many users, possibly many organizations, and entire networks of sensors. And the idea in federated learning is just to be smart about the way that we're processing all of this data that's coming to us in this distributed form. So rather than moving all of that data to some central location and training a model on the data once it's centralized, the idea in federated learning is to try to move as much of this computation to the edge as possible. Why would we do this? There are some benefits. One is that, devices like phones are becoming more and more powerful. They're basically small computers now. They can do a lot of processing at the edge. But this helps to reduce strain on the network. It allows you to more quickly incorporate new data that you're seeing. It allows you to leverage these massive, distributed computing infrastructures. And there can also be some privacy advantages for keeping the data in a distributed, siloed fashion rather than moving it to some central location. So over the last several years, I've been focusing on, with all of the wonderful members of my lab at Carnegie Mellon, developing some foundational tools for the field of federated learning. So this has been focused around things like efficiency, so developing communication efficient methods for distributed learning in massive federated networks. We've also focused a lot on the issue of heterogeneity, so dealing with the fact that data from these different devices or data silos might differ from one device, one client to another, not only in terms of the data, but also in terms of the underlying systems. So there might be some devices that you're trying to train over. Some are very new, some are very old, some have good network connection, some have poor network connection. So dealing with this heterogeneity in a rigorous way is a really important problem in the field of federated learning. And lastly, we've been developing tools, not just for federated learning, but for machine learning more broadly around issues such as privacy, and also things like robustness and fairness. And these tools we've been developing, we've been doing so in partnership with folks who are actually deploying federated learning in practice. We work very closely with teams at Google and Meta who are deploying these applications across thousands to millions of mobile phones. We've worked with partners at Semantic to develop tools for smart home anomaly detection. We recently won a large prize in developing tools for privacy-preserving pandemic forecasting across multiple hospitals. And throughout, we've had a big emphasis on developing methods that are open source and reproducible. So we've helped to, port our methods into things like TensorFlow Federated, FLSim, and Flower. We developed benchmarks for the field, like the LEAF benchmark. And I wanted to mention to the folks in this seminar in particular that I also helped to run a weekly seminar on federated learning. It's called the Flow Seminar. This is one of those silver linings, I think, that came out of the pandemic. So we started this, when a lot of the shutdowns were happening, and it's continued now. It's been, I think, 3 years that we've been running this seminar. So if you're interested in the field of federated learning, generally, I would definitely encourage you to check that out. It takes place over Zoom. It's open to the public. And we feature a different speaker speaking on the topic of federated learning each week. All right, so that's a little bit more about me and some of the research in my lab. Today, I'm going to focus on something specific in the field of federated learning, but this is not necessarily specific just to federated settings. It's actually an important and general trend in the area of machine learning. And that is that if you think about the machine learning pipeline, you maybe start with some raw data, you do some data pre-processing, you train a model from that data, then you evaluate how good that model is that you've trained, and maybe you perform some post-processing and finally deploy the model. This is sort of the classic canonical pipeline you might think about for developing a machine learning model and deploying it. Over the years, though, the way that we think about, where all our time is spent on this pipeline has started to change. So historically, and maybe this is still true to some degree, there has actually been, much, much more of our time that is spent on data pre-processing, even though we typically present this as sort of an equal pipeline. Getting all of this data, cleaning it, labeling it, takes a lot of time and energy. With the rise of deep learning systems, the hope, at least, is that we can remove some of the emphasis on data pre-processing, especially featureizing data, and we can automatically learn these representations. And here, the idea in these deep learning systems is maybe that more of the focus is on training. And indeed, training these deep models can be very expensive. Now, with the rise of pre-trained foundation models, these large language models and other foundation models, what we're really seeing is more of an emphasis on the problem of evaluation. And these are obviously all still important components. But for end users, for people who are deploying machine learning in practice, a lot of the time is now spent, taking one of these models and evaluating how effective it is for the application in mind, and maybe performing some post-processing, maybe doing some prompting, some fine-tuning, maybe compressing the model, making it more specific to the task that you're trying to solve before deploying it. So we're seeing this sort of evolving machine learning pipeline where something that we used to think maybe, was fairly simple, like just evaluating whether or not your model is reasonable for the task at hand, is actually becoming a very expensive process and quite a complicated process. And so in the talk today, I'm going to talk about two specific challenges around evaluation in large-scale machine learning systems. The first is thinking about the problem of evaluation in federated networks. And here, what we're going to see is, especially in large-scale federated networks, where maybe you're learning across thousands to millions of devices, evaluation can become very noisy and very complex, and it can be hard to get a reasonable evaluation signal when you're doing things like training or adapting your model. We're also going to, if we have time, talk a bit more generally about the problem of evaluating large language models. And this is something, even outside of the scope of federated networks, that is quite complex, and I think is going to continue to be an important area of research moving forward. All right. So let me start with this problem of federated learning. And again, please, if you have questions, please feel free to put them in the chat window, and I'll try to monitor that and make sure to stop. This is some work that's joint with some of my students and collaborators at Carnegie Mellon, as well as with some folks on the federated learning team at Meta. And I want to mention that specifically in this work, we're thinking about applications of federated learning in what is called commonly cross-device federated learning, where you're learning over a large network of devices, could be, mobile phones, sensors, wearable devices. These could potentially be very massive and very heterogeneous networks. And in these cross-device settings, the training and evaluation workflow typically looks like this. You have some hyperparameters that you feed to your model. So this could be, you're trying to train a model with some optimization method, and maybe you have some hyperparameters related to regularization or your learning rate or your batch size. And these hyperparameters are really crucial to finding a decent model for this problem. So you plug in some hyperparameters, you propose a hyperparameter configuration, you train a model on some clients, and then crucially, you evaluate that model typically on a separate set of clients. The reason this is often done is because these networks are so massive, you're often not guaranteed to be able to communicate with the same set of clients you use for training as at validation time. And this also helps to reflect what's generally happening in these networks, which is that you might train on one population of data, and then you deploy your model at inference time across all of the devices. So there might be some sort of distribution shift that's happening here. Okay, but the high-level workflow is very similar to what I described previously. You train on some clients, you produce a model, and then you evaluate how good that model is. Maybe you look at the error rate, for example. And you might do this many times, right? You might iterate through this until you find a good set of hyperparameters. So this seems fairly straightforward. What is difficult about doing this in federated settings? The first thing that's difficult is that there might be many more hyperparameters than you're used to seeing in a traditional sort of machine learning pipeline. And one reason for this is that in practice, it's become common to have maybe a set of hyperparameters specific to the server as well as specific to the client. So you might have a server-wide learning rate, maybe some hyperparameters if you're running something like Atom, which is a very common optimization method related to momentum terms. But then you also typically have hyperparameters that are specific to the clients. You might have learning rates or batch sizes, for example, for each of the clients. So the first issue is that in federated settings, we might just see more hyperparameters than we do in traditional machine learning pipelines. But perhaps more importantly, what we see is that there are significant challenges with evaluating whether or not these hyperparameters are good. And in particular, there can be issues where if you have a massive network of devices or clients, you have to significantly subsample the number of clients that you communicate with to evaluate how effective the model is. So you have this issue of client subsampling due to communication costs and the scale of the network. You're likely not going to be able to evaluate the model on every single client in the network. You also have this issue of data heterogeneity. So I mentioned this previously. This is very common in federated settings due to differences in the data from one client, one device, one phone to another. You might see data that looks a little bit different on each of the clients. And this can yield different evaluations on each of those clients. And the effect of this basically is that this can exacerbate this issue of client subsampling. Not only are you seeing a small portion of the network, but that small portion you're seeing might be biased in some way due to this issue of data heterogeneity as well as this issue of systems heterogeneity. So you can further bias things due to the fact that a certain subset of devices might be more likely to be able to give you a valuation signal due to some underlying systems properties of those devices. And finally, and this is something that I think is important to point out, because this is something that's often done in practical deployments of federated learning, that especially in the research sphere, I don't see this being done at all when people are evaluating new methods they're developing. In practice, when you're calculating these evaluation signals, you often do so in a way that is attempting to preserve the privacy of the clients. And so this is a very common tool that's used in practice in federated deployments, is that you apply something known as differential privacy. And what this is doing at a high level is adding some noise to the evaluation signal that you're seeing. So you add this noise to try to respect the privacy of the clients that you're gathering this evaluation signal from. But this is just another way that the evaluation signal that you're seeing might not be a perfect representation of the true evaluation across all of the clients. So the very broad question that we wanted to ask in this work is, how do these sources of noise potentially impact this simple process, this process that is ubiquitous across all machine learning pipelines. This idea that you have to tune possibly a set of hyperparameters to produce a good model for your application. Okay, and just to provide kind of a brief, illustration of what can go wrong. Imagine you have a subset of clients. Here I'm drawing them as phones. So you have some pool of clients that you're using for evaluation, and you have a set of potential hyperparameter configurations. The way that evaluation typically works is that you would look at these configurations, you would send them to all of your clients. Those clients would then tell you, how good is this configuration on my data? So there might be some ranking of the different configurations. You would aggregate that information and you would maybe select the best one, right? So you would average or, rank the results from all of these clients. And this would give you information about which the best hyperparameter configuration is. Now, what happens in practice is that we don't have access to the entire pool of clients to produce this evaluation, right? Due to issues of subsampling, right? Due to the fact that this network is massive, and we're not able to communicate with all of the clients, especially due to things like systems heterogeneity, due to the fact that some clients maybe don't have great network connection, aren't connected to power, have maybe very old phones. So they're not able to communicate results as quickly or at all. We see a subsample of this data. And so we're seeing a possibly biased sample of what the evaluation should be. And then additionally, we're adding some noise to this. Due to this privacy concern. So the result is that the final ranking that you see, the final sort of vote you have about which hyperparameter looks best could be incorrect, right? We saw previously that we should have picked this green configuration, but in practice, we picked this red configuration due to all these sources of noise. Okay, so this was our mental model of what could potentially go wrong in federated settings. And what we wanted to do in this work is see how realistic this is in practice. Does this actually happen in practice in federated systems? Can we quantify how big of an issue this is? And are there any ways to try to fix this issue? And we did this in the following way. So we looked at a few very common hyperparameter tuning methods. We looked at random search. This is probably one of the methods that you are familiar with if you've ever tried to tune hyperparameters. So often you're thinking about things like grid search or random search. Basically, you just randomly or in a grid select possible hyperparameter configurations. There are also, hyperparameter tuning is a whole sort of subfield of machine learning and optimization. So there's many, many other approaches that are popular. In particular, we looked at 3 other state-of-the-art approaches. One is this adaptive, this Bayesian optimization method, TPE, which basically I'm showing an illustration of it over here. The idea is that if you find in your hyperparameter configuration space certain hyperparameter configurations that seem particularly effective, take advantage of that knowledge, right? So maybe try to, in an adaptive way, select areas of this configuration space that seem particularly useful. We also looked at hyperband. This is another very popular method for hyperparameter tuning. The idea is sort of similar, except that you're not selecting configurations in an adaptive way. You're allocating resources to different configurations in an adaptive way. So if you see a configuration that seems from some initial training rounds to be very effective, you can continue to provide more resources to that configuration. And then we looked at this method Bob, which is basically a combination of these 2 approaches. So these are very common, approaches, sort of state-of-the-art approaches for hyperparameter tuning in non-federated settings. What we wanted to do is see how these methods perform in light of these possible sources of evaluation noise in federated networks. And this is actually, pretty easy to do when you think about the way that federated, pipelines run. You, in a federated setting, basically you can just directly extend what you have from a centralized setting, and then in centralized, hyperparameter tuning, you perform some training and evaluation, and then you use that as a, as information or signal for whatever hyperparameter tuning method you're running. So we can pretty easily sort of just take these methods that are designed for centralized settings and now implement them in federated settings. The main thing that we're changing is this box here, which is that we're performing evaluation, knowing that we have this sort of noisy signal that we're getting from the network of federated clients. Okay, so specifically the research questions we wanted to ask. We wanted to understand how this issue of subsampling affects the performance of these hyperparameter tuning methods. So how does the fact that we can't actually see all of the clients when we're trying to evaluate how good a model is or how good a configuration is, how does that affect the performance of these hyperparameter tuning methods? And in particular, how do these other issues possibly interact with or exacerbate this issue of subsampling? So how does this issue of data heterogeneity, which is very common in federated networks, how does that impact this problem of subsampling? This heterogeneity, again, can show up not just in terms of the data, but also in terms of the underlying systems. And in practice, we're often thinking about how to make sure that these evaluation signals are private. So adding some additional noise on top of this entire process. And, you know, sort of as a takeaway from this, we wanted to understand, how do the results that have been developed for centralized settings translate or potentially not translate to federated settings? And the concern here is there's been a lot of excellent work that's been done to develop these, you know, very efficient hyperparameter tuning methods in centralized settings. We wanted to understand how these state-of-the-art methods compare to very simple baselines in light of this possible evaluation noise. And I already showed the punchline here, but the punchline from these results, which I'll show in just a minute, is basically that if you apply these state-of-the-art hyperparameter tuning methods in federated settings, what you see is that they can perform quite poorly, oftentimes worse than very simple baselines like just running random search or grid search. And the reason that we think this is really important to point out is because even though this type of evaluation noise is very common in practice and practical deployments of federated learning, people are not typically, when they're designing methods in a research setting, thinking about these sources of noise. And so the concern that we have, and I think the thing that we're trying to point out here, is that it's important to try to mirror what's actually happening in practice when we're designing new methods for federated settings. So the simple way that we're looking at this in this work is showing that there is a pretty big delta between, you know, state-of-the-art methods designed in centralized settings and what you can see works well in federated settings. And the, you know, message that we're hoping to send is that this can apply not just to these hyperparameter tuning methods, but to many other methods that have been designed for federated settings as well. Okay. So I'm going to get into some of the results now and answer a few of these high-level research questions. But again, please stop me at any point if you have questions or if I can clarify anything. All right, so let's talk about the experiments in a bit more detail. We looked at a bunch of very common data sets in federated settings. CFAR10, FEMNIS, these are sort of smaller scale image data sets. We also looked at larger scale and a bit more realistic language data sets like Stack Overflow and Reddit. These are common benchmarks that folks use to benchmark the performance of methods in federated networks. And we looked at actually not a super large hyperparameter search space. So in practice, the set of hyperparameters you might consider might be significantly, you know, more than this. We're looking at basically a set of server-side hyperparameters related to this Atom method that I mentioned, as well as some client-specific hyperparameters related to the client-side learning rate and batch size. Okay, and let's just jump into some of the results that we found. So the first thing that we looked at is this issue of subsampling. So what happens if you are trying to, you know, evaluate the effectiveness of possible hyperparameters for, you know, one of these data sets and across this search space, and you're not able to access all of the clients to evaluate how good those configurations are? What you see, which I think is pretty intuitive, is performance like this. So on the, by the way, all of the plots today are going to be pretty much similar. So the y-axis is going to show the validation error. We want this to be small, so we want the error to be small. And on the y-axis, we're going to show some measure of evaluation noise. So here, what I'm showing, sorry, on the x-axis, we're showing some sort of evaluation noise. So here I'm showing the total number of clients that are used for evaluation. And what you see is that if you're able to use all of the clients for evaluation, the performance you get with something like random search does pretty well. It gets pretty close to the best possible set of hyperparameters you could have picked. But what you see is that as you start to do more subsampling of the validation clients, the performance of this hyperparameter tuning method starts to degrade. And this is somewhat concerning if you look at these numbers, because something like 1% is actually a pretty common number that you'll see in practice. If you have a network of thousands to, more like millions of devices, it's quite unlikely that you're going to be can communicate with even 10% of that network. You're likely going to be communicating with something like 1% or less. Okay, so this is something that's a much more realistic number. And you can see here that the error when we, perform hyperparameter tuning with this noisy evaluation signal starts to degrade. And this is something that we saw across all of the data sets that we looked at. We see this behavior that as you're performing more subsampling, the performance starts to degrade. So what we looked at next is how this issue of data heterogeneity can possibly make things worse. And what we did in particular is we took actually these data sets, which already have some form of inherent heterogeneity, and we tried to make them possibly more homogeneous. So we tried to take all of that data, centralize it, and maybe repartition it in a more homogeneous way. And what you see is that if you go back to the original sort of, more heterogeneous setting, you see worse performance. This is what you're likely to see in practice. If you start to make things more homogeneous, so things become more similar, some of the issues around subsampling are, not quite as significant. And so the trend here that you're seeing, which I think matches your intuition, is that this issue of data heterogeneity can exacerbate some of the effects that you're seeing of subsampling. Basically, if you have a small pool of clients that you're using for evaluation, and those clients might be very diverse in terms of the data on the clients, you might end up seeing a very biased sample of the network. Okay. This also can become particularly problematic with this issue of systems heterogeneity. So I haven't explained too much about sort of how this issue of systems heterogeneity can actually affect the evaluation signal. But what happens in practice is that, again, for various reasons, the devices, maybe they're, not connected to a power source. They have a poor, network communication. They have, maybe older hardware. It's just someone doesn't have quite as new of a phone. For various reasons, basically the way that these systems often work is that you set some timeout window and you set some constraints around whether or not you're actually able to pull evaluation signal from a set of clients. And depending on the system's characteristics, depending on things like how new the person's device is, and these various characteristics about whether or not that device is actually capable of performing evaluation, what you're likely to see is that there is a major source of bias here around the types of devices or types of people who are able to actually participate in evaluation. And what we did in this experiment is something that I think is pretty natural, which is that we looked at what if there is a similar sort of bias that occurs at training time and evaluation time. So the types of clients who are online, have newer devices and are able to participate in training, maybe those are also the types of clients that you see at evaluation time. So I think this is a very natural thing that you might see in practice. And the way that this can manifest is that the clients where they were used for training time, they're likely to be the clients that have a low loss or a high accuracy in terms of the model, because those are the clients that were used for training. So if we subsample the evaluation clients in terms of selecting clients maybe that were used at training time and thus are a good fit for the existing model, you start to see these sort of catastrophic behavior where as you increase this source of bias, you're basically seeing a narrower and narrower set of the population. And this can really start to affect the evaluation signal, and you can start to pick hyperparameters that are really suboptimal. So here you see that this can lead to quite poor performance in terms of the overall model that's selected. Okay, and lastly, and again, I think this is fairly intuitive, but what was interesting to us is just how quickly this can become problematic, is this issue of privacy. The fact that in practice, what you typically do when you're performing evaluation in federated settings is that you think about performing differentially private evaluation. So you want to ensure that there's privacy in terms of that evaluation signal so that you're not learning sensitive or identifiable information from the clients that you're learning over. And adding this noise and performing differential privacy can very quickly degrade the performance of these hyperparameter tuning methods. So even with a pretty loose definition of privacy. And I don't, have a ton of time to go into all of the details of differential privacy, but basically in practice, you think about this epsilon number. You want this to be small. This defines how private your system is. And the smaller this number, the better. Typically, you want this to be less than 1, maybe less than 10 at the most. What we see in these results is that if you're using, 10 or below, the performance of the method starts to significantly degrade. So we're only seeing sort of reasonable performance here for epsilon, 100 or infinity, so no privacy, basically. And this is something, again, that we saw across all of the data sets that we looked at, that even adding sort of a very small amount of noise for privacy can really tank the performance of these methods. So the final punchline from this is basically that now if you think about the performance of various hyperparameter tuning methods, again, these ones that have been developed for centralized settings, and you compare in a centralized setting the performance of these methods, you see what has been reported many, many times, which is that the state-of-the-art methods, things like TPE or Bob or Hyperband, improve upon the simple baseline of random search. But if instead you implement these state-of-the-art hyperparameter tuning methods in a federated setting, you start to see that the performance of these methods can be quite poor, in fact, significantly worse than just the simple baseline of random search. So here you can see on this noisy setting on the right, looking at a federated network, we see that Bob is basically not working to pick good hyperparameter configurations. And that both of these methods, Bob and Hyperband, are actually, significantly worse than the simple baseline of random search. And this is something that we saw. I just want to point out, these are not even, particularly realistic numbers that we're looking at here in terms of noise, in the sense that we're considering a very loose privacy budget, epsilon equals 100, and we're looking at subsampling 1% of the clients. So in practice, this could actually be much worse. Okay, so this is all sort of negative. Let me try to say something a little bit positive and think about how we could potentially solve this problem. So seeing these results led us to dig a little bit deeper and think about what else you could do in practice. If you wanted to find good hyperparameters in a federated network and you knew that you were getting this very noisy signal. And the idea that we had is actually something that we have seen, some of these federated learning teams doing in practice, maybe without much justification for why they're doing this, but I think that this study helps to motivate why this might be something you would do. What we did is we looked at how effective it would be to take some proxy data and use that proxy data, maybe data that's living at the server, to perform this process of hyperparameter tuning. And the intuition for why this might be reasonable is that in the plot, what I'm showing here is I'm plotting for various hyperparameter configurations, the performance of those hyperparameter configurations on 2 different data sets. So here we're looking at, say, CFAR10 and FEMNIS. These are 2 image data sets. And you can see, at least for these 2 image data sets, there seems to be a lot of correlation between which configurations are good. For these ones where we're going from a language data set to an image data set, there's not very much correlation. But intuitively, for data sets that are solving even somewhat similar tasks, we see a fair bit of correlation in terms of the best configurations across those tasks. And so this led us to develop the following method, this idea of using proxy data to perform hyperparameter tuning. And what you can see is that obviously the best data to use to perform hyperparameter tuning is the actual data set of interest, right? In federated settings, we don't necessarily have access to this perfect, clean data to use, right? Because we have all of this noise and the evaluation signal. But instead, we could use, maybe at the server side, a small amount of data from some other source that doesn't have all of this noise. So we looked at this. We looked at what if you use, say, FEMNIST to perform hyperparameter tuning for the CFAR10 data set. And you can see that the model that's selected tends to be not that much worse than what you saw for using the actual clean CFAR10 data set. And so this, led us to develop this I think, pretty intuitive method, which is to use proxy data to perform hyperparameter tuning. And just pulling this back into the previous results, we saw, again, sort of this catastrophic behavior of using the evaluation signal for performing hyperparameter tuning in federated settings, especially, when you start to actually care about reasonable amounts of privacy and you're performing subsampling of the data. What we're showing here is that using proxy data can, actually provide a very reasonable baseline relative to these other approaches. So, if we have anything less than, say, epsilon equals infinity, we're getting a major improvement from using this proxy data, using the FEMNIS data, for example, for the CIFAR-10 task. The caveat here is that the data sets have to be somewhat similar. So using, say, a language data set for CIFAR-10 does not seem to be very effective, but using similarly an image recognition data set like FEMNIS for CIFAR-10 is reasonably effective. And we saw this sort of behavior across all of the data sets that we looked at. Okay, so what are some takeaways from this? And then I can pause really quick to see if there's other questions before moving on to the other part of the talk. The takeaways that we want to point out here, one is that the study suggests a few best practices for this particular problem of federated hyperparameter tuning. One of the key takeaways is that in practice, it might be better to use simple hyperparameter methods like random search relative to these more state-of-the-art hyperparameter tuning methods that have been developed in centralized settings. If at all possible, if you have the ability to do this, what our results show is that it's really important to perform evaluation correctly. And by that, I mean, if possible, sample as large a number of validation clients as you can, and ideally find a representative set of clients. So if possible, try to address these sources of bias. This is often not really possible in practice. These are often hard constraints that we have on the system and the clients at hand. But if you have the ability to do this, this is something that we have found is important to do. If available, what our results show is that proxy data can be an effective solution to help to improve the performance of these methods. And I think that this is an area where there is a lot of other interesting follow-up work that can be done to understand when proxy data can be effective, what types of data sets could you use, what are the best ways to leverage this proxy data, can we rigorously show that hyperparameters from one data set can transfer to another data set. So there's a lot of ongoing work that my students are looking at in this area that I think can hopefully be an interesting solution. But more generally, the key thing we want to point out here, especially for folks who are developing approaches for federated learning, is that first, federated hyperparameter tuning is quite difficult. So in general, it can be very useful to develop new methods for federated settings that are simple, that don't introduce 10 new hyperparameters. And this is something that I think is, and I have been, guilty of this as well. This is a common thing that you see in practice, is maybe someone proposes the n+1 method for hyperparameter for federated learning that performs well on a subset of experiments and maybe introduces 2 or 3 new hyperparameters that you tune very specifically to get good performance. In practice, it's unlikely that you're going to be able to spend a lot of time and energy and resources being able to effectively tune those hyperparameters, especially in light of the evaluation noise that you see in real deployments. So this is just something that I think is important to point out for the field at large, that this problem is quite difficult, and that, one, I think it's potentially an interesting area to think about ways to improve this process of hyperparameter tuning, but that more generally, it's just a good practice to develop methods that are simpler if possible and reduce the burden of performing hyperparameter tuning. So let me stop here and see if there's any questions.
Yeah.
Oh,
we have a question. Just for everyone in the call, if you would like to ask questions, feel free to pull them in the chat or raise your hand, and I'll unmute you so you can actually ask your questions out loud. I guess I will read the first question in the chat. Can some measure of variability of the noise heterogeneity be incorporated into the centralized search methods? I guess in Bayes optimization, such thing can be incorporated. Also, is measuring this noise level hard?
This is a really great question. This is actually something that we are looking at currently and some follow-up work. So, and I think that you pose a question and also in some way pose our current answer to this question. So I think this is a great point. You could potentially try to model the noise that you're seeing in a federated network and then incorporate that noise model into some Bayesian optimization method. And this is something that has been done for different sources of noise previously in the literature for hyperparameter tuning. The thing that makes this difficult in federated settings is being able to crisply model and measure the sources of noise that you see. And part of the reason that it's so difficult is that you don't typically have the ability to understand what the true underlying population is, right? So if you had the ability to measure sort of the full population and understand how significant the source of noise was, you would ideally just use that entire population for evaluation. So the trick, and this is again something that I think is an interesting area of follow-up work, is trying to find sort of heuristics that can allow you to find a reasonable proxy for what that measure would be. Ideally, what you would do is you would calculate the full evaluation signal from all of the clients with no heterogeneity and no subsampling and no privacy. But these are often pretty hard constraints on the system. You have to implement it with these privacy constraints. You can't, communicate with a million devices at once. And so it's difficult to figure out what this true sort of baseline signal is from the population. It's a really great point, though. It's something that we're looking at in follow-up work.
I hope it answered your question. I would have actually 2 questions myself, if that's okay. And I don't see any other questions right now. First question would be about the proxy datasets. So you used some sort of more or less toy examples, right, for the proxy datasets. In practice, how hard is it actually to get proper proxy datasets?
That's a great question. So I think that it's a good point. We found this to be fairly effective, maybe partially because the data sets that we're looking at are pretty standard and are maybe, especially if you're thinking about the CFAR 10 feminist example, these are 2 data sets that are solving pretty similar tasks, image recognition tasks. In practice, I think this depends a lot on the particular application that you're looking at. If you're looking at a fairly standard machine learning application, image recognition, maybe next word prediction, other common language tasks, I think it's reasonable to assume that you would have some data that would be public at the server that you could use. In fact, for some of the folks that we've been working with, some of the teams deploying federated learning, they have some resources to generate or curate this data at the server. So they do spend some time, maybe even, paying for volunteers to manually create or label data. So oftentimes you can, devise or find a reasonable data set at the server. I think the trick is understanding how sort of the size of that data relates to what you have in a federated network. So in particular, you might have a very small amount of good data at the server that is different in some way than what you see at the edge. If you had a massive data set at the server and it was a good fit, you would just use that data, right? So it's often deficient in some way. And I think the interesting work to do in the future is understanding and making this a little bit more precise. How does the effect of the size of the data at the server and the quality of the data impact this procedure?
Thank you.
Cool. So I don't know if there's other questions. I'm happy to answer them. If not, I can. I have a few more slides here to show on this other direction around evaluating large-scale systems.
I think there's no current other. Another question. Are there any good measurements of quality and size of data in the context of federated learning?
Yeah, so this is actually something we have been thinking about this currently. There's been a line of work recently thinking about this, maybe not directly in the context of federated learning, but in the context of the problem of transfer learning more generally. So it's becoming more and more common that you might have, this is actually a good segue for the next part of the talk. You might have some pre-trained model that you're using, and that pre-trained model is maybe public, or you assume that it's been learned over some public data, and you want to take that large public model and fine-tune it on some private data that you have. This is very commonly done in federated settings. but this you can imagine for other applications of machine learning as well. And there has been some recent work which I think could apply to this question and to this setting, understanding how the quality of the public data or the public model that you have influences the private training that you're performing or the private fine-tuning that you're performing. So right now, I would say the measurements are, a lot of that work is more theoretical, and they're looking at very toy problems. Some of my recent work included to try to get a crisp notion of quality and size of the data. So there are definitely sort of nice toy problems where you can make this quite rigorous, and you can have a very concrete understanding of how the size of the data and different aspects of that public data affect the performance of private training. But I think what is necessary and what would be very useful in practice is to have some simple heuristics or measurements that you could take to quickly decide whether or not the public data you have is a good fit. Obvious thing to do is to run the experiment and see how it performs, but a more ideal thing would be obviously if you had some simple measurements that you could use in lieu of doing that. So I think that's a really interesting and important area of future work. And there's some work in semi-related areas, but the work that I've seen is looking at pretty toy problems so far. Yeah, thanks so much for the questions. I will just show you the last few slides here, but definitely happy to answer more questions if we have time at the end. So the first part of this talk was focused on evaluation in the context of federated networks, and we saw how noise from subsampling, privacy, heterogeneity can affect the evaluation signal and can significantly impact the performance of hyperparameter tuning methods in federated settings. We've also been thinking in my group about the problem of evaluation more broadly. And I think, like many folks, we've been spending a lot of time thinking about how the rise of pre-trained foundation models really changes things in the field of machine learning. And in particular, it can make this problem of evaluation very, very difficult. So I'm going to talk a little bit about that and about the tool that we've developed called ReLM, which can be used to better evaluate large language models. So the motivation for this work, I think, comes from, just looking at all of the recent excitement, but also potentially concern coming from these really exciting advancements in machine learning and AI. So you see, over the last year or two, these amazing advancements in the models that are being developed. But you also see some concern in how they're developed and how they're being used, and the fact that these models might leak personal information. So even though ostensibly they're trained over public data, they can memorize a lot of that data. So they might be memorizing, say, copyrighted data or sensitive information that is in the training data. And this can be easily compromised given how effective and expressive these models are. They are also, learning over potentially negative things in the training data. So they might have a propensity for propagating things like racism and bias, swear words. They might actually just be incorrect, right? They don't learn only good things. They learn everything that's in the data, some of which might be factually wrong. All of this has made it really important to try to evaluate what these models are doing. And I can give you, this is a very simple example. This is something that my student was looking at. He looked at the problem of, say, next word prediction. So maybe you're typing an email and you're writing this email to someone named Michael. You notice that there's a bug, and maybe the autocorrect, autofill is something like, what is the problem? If you change the person's name, you could get something like this. So you might get some more aggressive answer. And in particular, what we found is that depending on the name that you use, you have this biased outcome, that you're more likely to get this sort of more aggressive output of the model. So this is just a really simple example, but this might be something that you'd want to understand and practice. You want to understand what is likely an output of the model. Maybe you want to prevent against any output that looks like this, that maybe is producing this more aggressive text. what is wrong with you. But you also might want to understand whether or not there's any bias in these types of outputs, whether or not, this output is more or less likely given on the prompt or the input that you have. And so, there's tons of examples like this, right? So large language models, they can generate good content, they can generate bad content. And evaluation here is becoming a bigger and bigger problem because it can be very difficult to know what content is going to come out of the model and to try to potentially, first understand what that content might look like and then potentially try to address it. And in practice, a lot of the current solutions here are not really great. And let me give an example. So let's say you want to test something pretty simple, like you want to understand whether or not the model knows this one fact, whether, what was the date that George Washington was born on. So this is a pretty simple fact. You can imagine this being many other things, but the high level idea is you want to test the factuality of one of these models. And, if we're doing this, we might just go to Wikipedia and find the date that George Washington was born, which is February 22nd, 1732. But if we want to test whether or not a large language model knows the output of this, there are two common ways that people perform this testing right now. One is that they generate their own sort of multiple choice test, right? So they create their own prompt. The prompt might look like this: George Washington was born on blank, ABCD. They come up with the ABCD and they try to have the model select from A, B, C, or D. This is a really common approach in a lot of these existing benchmarks for large language models. They have these sort of very complicated prompts that they've come up with. And, ideally the model would pick the correct answer from amongst this list. But the problem with these tests, maybe this is, sort of obvious, but the response here depends a lot on how you set up these prompts, the A, B, C, and D. And you can imagine that maybe this test is more interesting, but you could have come up with a very silly test. And maybe the model correctly predicts D, but it's because these other answers are just not that great, right? And so this has been pointed out as an issue with this possible form of testing. And one way around this is, instead of coming up with this complicated specific multiple choice test, maybe you could just see what the output is of the model. And so you might say George Washington was born on blank and let the model generate the text after that. And the issue with this is that there's a bunch of stuff the model could spit out here. It could say things that are technically true, but not really the answer that we want. It could say George Washington was born on this day in 1732. That's a very reasonable way to finish this prompt, but it doesn't tell us very much useful information. It could say George Washington was born on a farm. Right, so these things are technically correct, but they're not super useful in terms of evaluating the factual correctness of the model. Okay, and so what we came up with in developing this tool ReLM is to basically produce a regular expression engine for these large language models and for the output of the models. And so what we can do is we can constrain the output of the model to look like a specific format. So for example, if you're testing whether or not the model understands the date, the date that George Washington was born, you can constrain the output of the model to take a particular form, the form of month, day, year, for example. And what's interesting here is that if you actually, plug this into ChatGPT, you see something that is incorrect. And so this is not to say that, one form of the test here is always better than the other, but that if you want to be able to quickly try to evaluate whether or not these models know what we think they know, it can be useful to try to look at not just this very highly curated test or this, possible output that could have any sort of answer, but to have something more constrained in terms of evaluating the effectiveness of these models. Okay, and so this is, I'll just present these slides pretty quickly because I know we're about to run out of time, but this is the motivation for this tool that we developed called ReLM, which can allow you to devise regular expressions for language models. This can be useful for a bunch of things. It can be useful, by the way, anytime you want to generate output from a language model that has a very specific type of output. But this, it turns out, can be very effective specifically for evaluating these models. So for understanding whether they have memorized specific information, maybe credit card numbers, for example, whether there are sources of bias that the models exhibit, whether they can produce output that contains possibly toxic or offensive content, and these sort of, factual understanding tasks, which are very typical in existing benchmarks. So in developing this, the high-level idea, I don't have time to go into too many details here, but the high-level idea is basically that you can, put in sort of a regex pattern for what you want the output to look like. What we're doing under the hood is an efficient way of, mapping through and sampling from the output such that we're constrained to find output of this particular form. And there's a lot of details I don't have time to go into here, but the high level takeaway is that this can be very useful for evaluating models and doing so very efficiently. So we can show that we can extract information much more efficiently than existing baselines. And we can also find toxic behavior much more quickly, for example. So these are two of the specific use cases that we looked at. This can, just a few quick takeaways here, this can allow us to much more quickly extract memorized data to expose sources of bias. We can more efficiently find toxic behavior of the models, and this allows us to effectively evaluate sort of the understanding of the models much more efficiently and effectively as well. So if you're interested in taking a look, I'd highly encourage you to take a look at the code or the paper which was presented at the Machine Learning and Systems Conference this summer. So thanks, that's all I had. I'd be happy to answer questions if there are any additional questions.
Thank you. I will take maybe the occasion now to invite everyone to the next BCast in 2 weeks. It's going to be on the 26th of October. We have Marianne Berklest from KU Leuven, and she'll be talking about heterogeneous multi-core systems for efficient edge machine learning. Now to questions, if anyone has any questions. The format is the same. So maybe I will start. So I'm actually interested in this toxicity because you mentioned that you reduce it as well. So I roughly understand how you're doing the regex part, and then how do you actually? I think you just went through the slides. How do you actually do the other part?
Yes, you have some, regex query that you might use. So for example, do I have the example of the toxic search here? There might be some sort of toxic, let me see, task that you're trying to, I don't think I have the example here. Anyway, there might be some sort of toxic, oh yeah, here. There might be some sort of toxic, I don't know, this is a sort of censored example. Let's say you have something very simple, like you just want to see if the model can say that someone's an idiot. One thing that you might have in practice is that there could be many variants of this. And so you want to quickly understand whether or not this output exists. And so what something like a regex query could allow you to do is look for any output that contains the word idiot. So there might be many different, examples of a sentence that contains the word idiot, many different, instantiations or variations on the text. And so what we're doing under the hood is we're enumerating all of these possibilities, and then we're quickly sampling from the output to see whether or not these, possibilities exist in the output.
Okay,
yeah.
Thank you. Do we have any other questions? Okay, I don't see any. So thank you again for presenting for us, Virginia, and hope to see you all in 2 weeks.
Wonderful. Thanks so much. Thanks again. See you all.